So today we'll be learning how to do these beautiful Gerstner waves in Godot. So let's get right on it. Now if we open the Wikipedia for this trochoidal wave, Gerstner wave, I'm not really sure how to pronounce that, but if you open the picture here, we can see that the particles of the wave are all moving in a circular motion. So that's gonna be our key, and that's what we're gonna try to emulate in our shader. So let's start by adding a mesh. It's gonna be a plane mesh. If I zoom in here, I'm just gonna go to wireframe mode so we can see what's happening, and we're gonna subdivide this a little bit so we see what's going on. So let's make it bigger first of all, 10 by 10, and then let's do 30 to 32. So we want to create a shader where we move the vertices in a wave-like pattern. So let's start by adding a material here, and it's gonna be a shader material, and we're gonna make our own shader. We can call it, G-Wave, sure. And we're gonna clean this up. Let's start first by trying to make a wave. So we know we can use the sun function to make something that looks like a wave. So if I say vertex.y is sine of time, everything is gonna start moving up and down. However, we want the movement to be dependent on the distance it is along the horizontal plane, so our x and z axis. So let's say plus vertex.z. And now we can see that we have a wave-looking thing that moves in our z direction. Right now, we're only moving the vertices up and down. And remember, we also have to make it so that it kind of moves horizontally as well. So for the vertex z, we can say the exact same thing, except we're gonna use the cosine. And then we get a nice wave like so. And if you track the vertices, you will see they move in a circular direction like we want. Now, if we want to change the direction of the wave, we have to change all these to .x instead. And now it's moving that way. And if we want it to move in the direction between x and z, then we have to use both of them at the same time, but we gotta weigh them down by the direction. So I'm just gonna comment this out for a moment, and we're gonna declare a direction vector. It's gonna be a normalized vector 2, and let's say 1 and 0. This direction should now be moving in the x-axis. So to do that, we have to weigh down the vertex x by the direction x, and vertex z by direction y. So now we can see if we flip this around, everything works as expected. And then we have to do the same thing for the x and z components as well. So let's first copy out this phase that we made here and make a new float. And then we can use it inside here. Now we want to do the same thing for the x and z components. So let's put in the same phase that we used and weigh down by the direction x, and do the same for the z position using direction y. And now you can see, even if you put some in-between value, the wave looks correct. Now we can also do this in one line instead. So instead of passing just .x here, we can say .xz, and instead of passing the component, we can just pass the entire vector, and that does the exact same thing. Now, if you've seen my video on dot products, then this multiplication and summation of these products here looks very familiar. And actually, it's just a dot product between the direction and our vertex horizontal plane. So there you go. Now let's clean this up a bit. I'm gonna make a new function called Gerstner, and let's just gonna take a position and direction. And it's gonna return a vector displacement, and then displacement.y is gonna be equal to this, and displacement.xz is gonna be equal to this. We can delete this. We can take the phase up in here. This is gonna be an xz position that we pass in, and then we return the displacement. And here we're gonna say vertex is plus equals to Gerstner, and we pass in the position and direction. Alright, so this is a bit more organized this way. And actually I'm gonna make one more function. I'm just gonna call it wave, and it's gonna return again a displacement. Just gonna call Gerstner from up there. We're gonna pass in the position, so we have to pass in position. And actually I'm just gonna hard code the directions for now. So let's say we wanna move it like so. And then we have to remember to always normalize the direction here. So let's do this quickly and then return that displacement. And then instead of doing this, we can just call our wave function and pass in the position. So we can get rid of this and just double check everything still works, and it does. Now the reason I've done this is that we can very easily add multiple waves together. So let's say we want to add another wave. We can just say displacement is equal to another Gerstner wave. And we can say this one is going to be in the opposite direction. And when we add it up, you can now see that we have one wave traveling in this way and then another wave traveling this way. So that's great, and let's continue on to adding some texture to this. And actually, before we add some textures, let's add some parameters to our wave generation so that we can control the amplitude and the stiffness of the wave. So let's say we're gonna pass a float for amplitude, and a float for steepness. So let's say this one is gonna have an amplitude of 1 and stiffness of 0.5. Or actually, let's just make the stiffness equal for all waves for now so that we don't overcomplicate things. So we just pass in the amplitudes, and then the displacement on y is gonna be multiplied by amplitude here. So now if we scale this one down, you can see that this wave is having its full amplitude, and then there's a really small wave traveling in this direction. As for steepness, let's just declare it as a uniform. I'm just gonna set it 0.5 for now. And then if we open the shader here and under parameters, we can change the steepness of our wave. So you can see right now it's very pointy, and then if we put it down, it gets more round at the top. Just gotta make sure that we say it goes from 0 to 1 here. There you go. So now this only goes between 0 and 1. So I'll just leave it about 0.2 for now. That looks good to me. Actually, another thing that I want to have is a frequency for each of these waves. So let's add a float for frequency. And then let's just pass 1 for each of these for now. And then for our phase, we are gonna multiply it by the frequency. Like so. And then let's say we want to increase the frequency of this small wave here. Just gonna set it to maybe 0.3 so it's more obvious. And then do 2. And now you can see we have twice as much waves in one direction than in the other. So that works fine. And I'm just gonna reduce that back to 1 for now, and then we're gonna play with it later. Alright, so let's think about texturing this wave. So what we can do is declare a uniform color. Let's call it color, and it's gonna be source color. And then under the fragment, we can just say that the albedo is equal to that color. And let's switch back to normal view. And then if we open this up, we can see here we can just pick a color for our wave. Now most of this color is going to come from the reflection of the sky. So let's set the roughness to 0.01, let's say. And then it's most going to be reflecting the sky. So even if I tune this all the way down, you can see it has like a bluish color. So let's leave this as it is for now. And then you will notice that the reflections don't really look correct. In fact, it looks like it's just a flat plane, because in reality it is a flat plane, and our model here doesn't know that it's being curved. So we have to calculate this normals ourselves. So let's do that. To calculate a normal, we're gonna do something interesting. We're gonna be sampling points that are just slightly offset from one of these points. And we're gonna do this for all the points here on the mesh. Then we're gonna sample a point slightly to the front and to the side and use a cross product to get a normal. So what do I mean by that? So we started off with a flat plane, and then this transformed into a wave. Now let's say we pick a point here. That point, when it's transformed, becomes a wave over here. Then we're gonna take a point slightly to the front, see where that hits the wave when it transforms, and then one point here to the side, and see where that hits the wave when it transforms. Then we have two vectors, forward and left, and then we can use a cross product to calculate a normal. So let's do that. So let's start by declaring our original position, and we can just say that is the vertex .xyz, and then inside here we can use that position as well, why not? And then we want to get the position that's slightly to the front. So let's call it forward position, and it's gonna be our original position plus a vec3 in the forward direction, so that's -1 on the z-axis times a small sampling distance. And let's also declare that here uniform float sampling distance, and I'm just gonna set it to 0.01 for now. So let's use that here, sampling distance, and then the same here, we're gonna call it left position, and it's gonna be on the -x, like so. Now we want to get the position of the transformed points on that wave, so we can use the same wave function again for these 2 points. So let's say this is wave forwards, and we're gonna say wave using the forward position .xz, and then the same for the wave left, and we're gonna use the left position xz. Now we want to compare these two to our actual vertex offset. Now remember, the wave function gives us the displacement, so we also gotta add it on top of our actual sample position. So forward position plus the wave, and left position plus the wave. Same as we did here. It's vertex plus this displacement, right? So now we gotta construct our forward and left vectors. So let's say vec3 forward vector. It's gonna be our wave forward minus vertex, and then the same for our left vector. So left vector, wave left minus vertex. And now we can use a cross product to calculate a normal. So let's say normal is equal to cross between forward vec and left vec. And now you can see that our reflection looks correct. So that's a great little trick on how you can calculate normals. Now let's just make sure we normalize the cross product. So normalize, and then we can increase the subdivisions now since everything looks fine here. So let's do 512 by 512 just to get a little bit more detail in our mesh. Now this doesn't look particularly like a wave at the moment. So let's add a bit of noise to it. I'm just gonna turn off the grid here, and then we can sample a noise texture. So let's declare a uniform sampler 2D. We can call it noise. And then if you go to our shader parameters, we can open a noise, say it's a noise texture, and then we're gonna assign the fast noise light, make sure it's seamless, and we can play around with these parameters. I'm just gonna use this cellular here, and then we wanna add some offset also in the vertical direction using that noise. So let's go to our Gerstner wave function, and let's say we have a float for noise value, and we're gonna sample our noise texture using some coordinates. Now the coordinates we're gonna use have to be between 0 and 1, because that's how UV textures work. However, our mesh is 10 by 10 wide. So how can we get the coordinates that we want? So let's draw our mesh here. So it has a pivot point in the center, and then it goes to -5 to +5, whereas our UVs go from 0 to 1. Well, if we just divide everything by 10 on the edges, we get -0.5 and 0.5 here. And then if you add 0.5, we're gonna end up with a 0 here, with a 1 here, and 0.5 in the middle, which is exactly the corrected and expected values that we want from our UV maps. So we can divide our position by 10 and add 0.5. And then for the noise value, we can just use the R here, because the noise value from black and white texture of our noise just has grayscale values. So we can just take the red ones, for example, here. Now, what we want to do here is add it to our Y displacement. So let's add plus noise value. And now we get, well, something gooey and weird looking. So let's make sure that this noise value also has a way to be controlled. So let's also declare a uniform noise intensity, and I'm just gonna set it to 0.2 by default, and it's a float. And then I'm just gonna multiply our noise value by noise intensity. So straight away this looks much better. And if we open our shader parameters here, we can play around with the noise intensity. I'm just gonna say it's also a hint range from 0 to 1, and then I can scale this up as I see fit. So I'm just gonna leave it around 0.25 here. That looks pretty good to me. So now we can play around with our waves a little bit. So I'm gonna add here one more wave, and I'm gonna play with the amplitudes a little bit. So let's say this main wave is gonna be 0.6, and then the other two are gonna be 25 and 25, and then we can maybe add more frequency to this smaller wave. So let's say 1.3 and maybe 1.8. And now we have some variety here. And now one final thing that I really think helps sell the illusion is to make this noise pattern also move in the direction of the wave. Now, how do we do that? So here we were sampling the noise value from one position. Now this is static. So what we can do is add a time and multiply it by the direction. Now you can see everything moves really fast. So let's just also multiply it by a low value, something like 0.02 maybe even more. There we go, 0.05 seems to work fine. Now this instantly makes everything come alive and look like an actual wave. So I played with the settings a little bit, and I got something that I like. So these are the 3 waves that I made. So just a bit of different frequencies and amplitudes, and we can get a very interesting looking result. And then we can also add some rim color to it. And what rim does, I'm just gonna make it incredibly high so you can see what it does. And it just gives us this kind of light that reflects very nicely once we are looking at it from a steep angle. So I'm just gonna tune that down to 3 and keep it like so. Now I really like the look of this. So that's what I'm gonna keep it as. And just like that, we have a beautiful looking Gerstner wave. So I hope you can play around with this. Maybe you can get some cool results. And yeah, I would love to see what you can come up with. So I hope you learned something new, and I'll see you in the next one.